This is our two-sample t-test with unequal variances. So we're going to use this one when we want to compare two population means, and we have independent samples because our samples are supposed to be independent, and we know the sample. Notice here I have sample emphasized, the sample variances, because t-tests are always for sample standard deviation variance. Now when I say variance, or it could be standard deviation, because standard deviation and variance are the same thing. Standard deviation is just the square root of variance, or variance is standard deviation squared. So it doesn't matter which one they give you. Okay. You'll also notice here it says unequal variances. That's because there's another test you can do if the variances are equal. It turns out though that even though that one is slightly more powerful, slightly more accurate, the difference that you'll get between if you use this test, that test, and this one is so minuscule it doesn't matter. Okay, so this unequal variances works for all the times when the variances aren't equal. It also will be close enough when your variances are equal. Okay, you have conditions for it, in that both populations have to be either normally distributed or have a sample size of at least 30. The null hypothesis will be that the two population means are equal. Makes sense, that's our good status quo. The alternative is you can do that the first mean is less than, the two means are not equal to, or the first mean is greater than. For our test statistic, it's a t-test statistic again. We do the difference in the two sample means divided by the square root of the first variance over the first sample size plus the second variance over the second sample size. Some people wonder why we're suddenly doing variance as squared instead of just standard deviation, and the reason why is it's inside the square root, and so when you take the square root of it, you kind of get back to that standard deviation. Okay. And we have to use a Satterthwaite approximation of degrees of freedom. You'll notice this is a very long, very complicated looking formula. Surprisingly, that's the easiest, best way we can find to find our degrees of freedom for this test. Okay. But luckily, we're going to put it in our calculator. Okay. And for our p-value, remember for everything we've done, our p-value is just always the area in the tail. Or tails. So if I have the alternative hypothesis, mu1 is greater than mu2, so my first mean is greater than my second mean. Well, because it's a greater than sign, I will look for the area in the right tail. Sometimes we like to write it as a difference instead, because that's really what we're doing in our test. So it's mu1 minus mu2 would be greater than 0. Or if you have the first mean is less than the second mean, when you subtract them, mu1 minus mu2 would be less than 0. And not equal to would just translate to the differences are not equal to 0. But again, greater than means right tail, less than means left tail, and not equal to means you'll have to find the area in both tails. So for our calculator, we'll pick our test. We'll want a two-sample t-test, and we have to choose pooled no or pooled off depending on which calculator you have. Again, the reason why it's pooled is that's if you want to say you have equal variances. Again, that's slightly better if you have equal variances, but our unequal variances really works for every situation, so we'll just go ahead and use that. Let's try it. A production supervisor at a major chemical company has to determine which catalyst, XA or ZB, will maximize the hourly yield of the chemical process. He takes a sample of 5 hours for each process and finds that for catalyst XA, the sample means 811, sample variance is 386. Notice again, S squared means it's variance, not standard deviation. So I like to go through and write out all my info. So for catalyst XA, we have a sample size of 5 and a sample mean of 811 and a sample variance of 386. For ZB, we again have a sample size of 5. That sample mean is 750, and that variance is 44. So just writing it all out like this helps me keep track of everything. From previous experiments, he has good reason to believe that the yields are normally distributed. Okay, well that's useful because on our conditions, those are small sample sizes, but my data is normal for both, so we're good there. Conduct a hypothesis test to see if the two catalysts have different population means. It didn't say which one they think is bigger, it just said not equal to, just said different. And we want to use alpha equals 0.01. Okay. Looking at these box plots, I would guess that the population means are going to be different. That seems pretty different, don't you think? So, hypotheses. The null hypothesis is always just going to be that the two means are equal. Now you can call them mu1 and mu2. I actually like to use abbreviations that mean something to me, so I'll call it mu for xa equal to the mean for zb. So that will be the null that they're equal. The alternative, that's the interesting part, it says different. It didn't say which one they thought was higher, so we'll just say not equal to the mean for zb. Next is find your test statistic. And for this, we pull up our calculator. So I'm going to do my stats again. I'm going to go over to test, and I'm looking for something that seems like 2 samples and a t-test. So look here, 2 samp t-test. That's what I want, number 4. Okay, I'm going to put in my summary statistics. So my first mean is 811. My first standard, oh, notice here, this one actually wants standard deviation and not variance, so I do need to come find that. So if the variance is 386, then the standard deviation will be the square root of 386, which equals 19.64. And for my ZB, that will be the square root of 484, which gives me 22. So coming back to my calculator, my first standard deviation is 19.64. My sample size is 5. Now for my second set, ZB, we have a sample mean of 750. My standard deviation is 22. My sample size is 5. Notice we get to choose our alternative. So my first mean is not equal to my second mean, so do the not equal to. We want pooled to no. And you can calculate it or draw it. Let's see what happens if we draw it. So I need to pick one of these where it's actually a bigger p-value. But our test statistic is 4.6, which would be way over here, so it's shading in that tail and you can't even see it. So my test statistic is t equals 4.6251. That means if I was to draw it out, here's my 4.62. I would want to shade it the area to the right, but because it's not equal to, I would also shade the area to the left of negative 4.62. And my total p-value for both tails equals 0.0018. This is what happens if you do the calculated version. It tells you your alternative is the two means were not equal. My test statistic is 4.62. My p-value is 0.00175 or 0.018. And it just gives you the summary information again. So coming back over here, I have my p-value of 0.0018. So p-value is smaller than alpha. So my p-value is smaller than alpha. So I will reject the null. I have evidence for the alternative. Okay. So then what I write up for my boss is we found evidence that the population mean hourly yields are not the same for XA and ZB. Then at this point I would go back and investigate and say, well, okay, I know that they're different. Now let's try and figure out maybe which one would be better. There's a problem for you to try. We can do this next problem now. So a current research topic in sports biomechanics is reducing the impact of the heel strike force when running on a treadmill. So this data set, heel strike, contains measurements of the heel strike force in newtons of runners on both the standard and down. Conduct a test to see if the damped treadmill reduces heel strike force. Okay, so we have here our histogram of our standard, our histogram of our damped. We also have box plots. So it looks like standard is slightly higher, which means damped is lower, and that's what we're hoping for, is that damped would be lower. I also did my normal quantile plot. I did this one in a different program, and so it actually puts in my straight line for me to compare it to. But I would say even though none of these are exactly, they're not that bad. Like they kind of follow the general shape. They're mostly symmetric. We're fairly close to the line. I would say all of this data is normal enough. You'll also notice I gave you all of this computer output. Okay. So notice it was doing a t-test for two independent groups with unequal variance. We have our summary information for our standard and damped treadmills. So let's go through and fill everything out. So I didn't tell you alpha, so let's choose alpha equals 0.05. Then I want you to write down the summary info. So for standard, let's see, if I write down an order, I have mean. So my mean for standard is 765. My standard deviation for standard, that could be confusing, SS, is 50.82. And my sample size for standard equals 50. For the damped, my sample size was 50 again, so, and for my damped is 50. My sample mean for damped is 740.75, and my standard deviation for damped is 39.68. Okay, my conditions has to be normal or big sample sizes. These are actually both big sample sizes. Okay, and normal enough. You only need one of them. So we're like doubly good here. Okay, then you need your hypotheses. Okay, so again, we want to know, is damped better or is damped reducing it? So is damped smaller? So we're looking for damped smaller. But you have to come back up and look and see which order they did it in. They did standard minus damped. Okay. So if we have standard minus damped, and damped is supposed to be smaller and standard is supposed to be big, then that means we have big minus small, or I guess we don't have to do that, sorry. Old-fashioned technique there. We want damped to be smaller, so our null will always be that they're equal. So the mean for standard is equal to the mean for damped. And the alternative, we want the damped to be smaller, so the mean for standard has to be bigger than the mean for damped. Just make sure you do everything in the same order. So if they do standard minus damped here, standard minus damped here, standard first, damped second. Our test statistic, we just get a read off of our output. So test statistic, t equals 2.67. Degrees of freedom, it does tell me degrees of freedom, so 92. P-value, 0.0091. And decision. So my p-value of 0.0091 is smaller than alpha equals 0.05. So I will reject the null. Notice we are always rejecting the null, but our conclusion will always be in terms of our alternative. So we found evidence that the population mean, well, let's make it even more in layman's terms. So we found evidence that the average heel strike for the damped treadmills is less than the average for the standard treadmills for all of the treadmills, not just our sample. Now, our 95% confidence interval for the difference in the means is what? We haven't talked about how to find a confidence interval for it, but look up here in my output. Notice confidence interval. I don't even have to know how. I can just read it off of my computer output. So it looks like it's 6.2 to 42.4. That seems like a huge difference to me. This means we're 95% confident that our true difference in the population means is between 6.2 and 42.4. Another way to say it is we're 95% confident that the population mean for our standard treadmill is between 6.2 and 42.4 newtons higher than the population mean for the damp treadmill. Just as a kind of a side remark here, I think this experiment would have been a lot better if they did matched pairs or paired samples. So each runner would have tried both types of treadmills, and that would eliminate the bias of the actual runner, because I would think people would run with different amounts of force, like based on your weight or just kind of the different stride you have, you're going to run differently. And so if you had each runner do both treadmills, you'd get rid of the effects of just the individual runner. But they didn't do it. That's okay. We can still analyze it. It's still good. We can't always do matched pairs. We often don't have enough time or money, or we're just not set up that way. And so we can always do the independent samples. But if you have the time and money, doing matched pairs would have been better. And there's another now you try problem. Okay. And I just want to walk you through this confidence interval. So for our hydrogen peroxide example, the 95% confidence interval for the difference in the means, notice it gives me the population, or the confidence interval here. So negative 4.5 to 0.6. So negative 4.5 to 0.6. So this would mean we're 95% confident that our true difference in our population means is between negative 4.5 to 0.6. Notice this is going to include negative numbers and positive numbers. So if it's negative numbers, that means one is better, and if it's positive numbers, that means the other one's better. So because we're getting highs and lows, we're not really sure if the high level or low level is better. This is just another sign that they're probably not different. They're probably about the same. And as you did this test, you would have noticed that you had a big p-value and you failed to reject the null. Okay, and so this makes sense because in the actual hypothesis test, we failed to reject the null hypothesis. So we did not have enough evidence to conclude that the population means were different. And again, here in my confidence interval, I'm thinking one's bigger, I'm thinking the other one's bigger. We just don't know, so we don't really have enough evidence to say that our population means are different. And just one last note, there are other two-sample tests that you can do, but they rarely actually come about in practice. Because the two tests are, first one, if you happen to know the population variances, you can use the two-sample z-test. But when do we ever know the population variances? There's a few examples where you can say, I think this is what the population variance is, but that's so rare that you almost never use it. If you did, though, this would be our test statistic. Okay, you'll do the difference in the sample means, you'll do the variances or sample sizes, add them together, take the squared, and you'll use the standard normal distribution or the z-distribution. If you have the sample variances and you have a good reason to think that the variances are equal, we use a two-sample t-test with pooled variances. So what that means is we do this pooled variance, this SP squared here. This is called our pooled variance. It's just a weighted average of our variance, and then we put that inside the square root. Okay? And the degrees of freedom is a lot easier. You'll notice this degrees of freedom is a lot easier than the degrees of freedom that we did. This is why this test has stuck around for so long, because it was a lot easier to compute by hand. Okay, the pooled variances, if you think it has equal variances, is slightly more accurate if the variances are equal. Otherwise, the unequal variances method is much better. So if you're not sure if the variances are equal, we would still use unequal variances because it's our safe choice. But even if the variances are equal, unless you have really small sample sizes, you get almost the exact same result with the unequal variances, even if variances are equal. So many people just always use the unequal variances, and so because of that, in this class, we're only going to use the t-test with unequal variance.